Hey everybody, today we're going to go over some examples of different chemicals in the various families of salts. The first family of salts is the binary salts, which is just a metal and a nonmetal, but the nonmetal cannot be oxygen. Remember too that we named the metal in its entirety, but turned the ending of the nonmetal into "ide". So let's start with potassium chloride. First we're going to draw the symbol for potassium, which is K, and we're going to draw the symbol for chlorine, which is Cl. Since salts are ionic compounds, these atoms are going to be ions, which means that they are going to gain or lose electrons. Remember from the lecture notes that the metals are going to lose electrons and form positively charged cations, whereas the nonmetals are going to gain electrons to form negatively charged anions. The reason these atoms gain or lose electrons is so that they can become stable through the octet rule. So for potassium, we're going to draw the Bohr model, and since potassium is in group 1, it's only going to have one valence electron. So let's go ahead and draw that. So potassium has 19 protons. We're not going to get too detailed with that because it'll just be messy. So I'm going to have 2 electrons, my first shell. I'm going to have 8 more in my next. I'm going to have 8 more in my next, and then my final shell is going to have just 1 electron. Okay, and since chlorine is in group 7, it's going to have 7 valence electrons. So chlorine has 7 protons, and in that first shell I'm going to have 2 electrons, 8 electrons in the next one. Then I'm going to have 7 electrons in that final one. Okay, and we can now see that potassium is going to be able to give up 1 valence electron to chlorine. Alright, so we're going to take that, put it over there, and now what I can do is I can redraw this. So I've got potassium, I've got chlorine, so I've got my 19 protons, 2 electrons, sorry for the sloppiness, and I've got 8 electrons on that outer shell, and with chlorine I've got 17 protons again, and I'm going to have 2, 8, and 8. Okay, so now these are happy, okay, because of the octet rule. There's a little smiley face showing that they're happy. However, the charges on these are no longer neutral. So if I compare my number of protons to my number of electrons for potassium, I've got 19 protons versus 18 electrons. So that means that my potassium is now going to be positively charged. All right, and then I can check out my chlorine. My chlorine's going to have 17 protons versus 18 electrons. So it is going to have a negative charge now. All right, and because opposites attract, the potassium and the chlorine, or sorry, the chloride, I should say, are now going to be able to combine to form potassium chloride, or KCl. KCl, also called potassium chloride. So the Bohr model is a really good way to visualize what's happening on an atomic level, but it can be pretty meticulous to do this for every single problem. So we can use something called the Thorpe's crisscross method to help us speed up the process. So first we're going to write the symbol for potassium, and we're going to write the symbol for chlorine, Cl. So since K is in group 1 on the periodic table and it's a metal, we can give it a +1 charge since metals always donate electrons, so they will form positive cations. So we're going to give it a +1 charge. And the +1 charge comes from the fact that it needs to give up 1 electron to reach the octet rule, as we saw earlier with the Bohr model. Chlorine is in group 7 and is a nonmetal, so we can give it a -1 charge since nonmetals always gain electrons, so they will form negative anions. So we're going to give it a -1 charge. The -1 charge comes from the fact that it needs to gain 1 electron to reach the octet rule, and you can look back at the Bohr model earlier to see what I mean by that. Now that we have potassium +1 and chlorine -1, we can crisscross the superscripts and turn them into subscripts. So we're going to take this and bring it down here, and we're going to take this and bring it down. All we're doing is crisscrossing. And so now what we have is K with a subscript of 1 and Cl with a subscript of 1. And we're no longer worried about positives or negatives. It's just going to be whatever the number is. And since both of those are 1, we can further reduce this down to KCl, which is the same as before, potassium chloride. So you can see how this is a whole heck of a lot easier than having to do all your protons and electrons and stuff like that. All right, so with my binary salts, my hazards are going to vary, okay? So I'm going to have to look them up. I'm going to have to pretty much tell my chief or my hazmat supervisor, hey, I'm going to have to look these up. I can't just predict it. However, there are 4 out there, 4 binary salts that do have some predictable hazards. They're the nitrides, carbides, hydrides, and phosphides. I'm going to write that out. The nitrides, the carbides, the hydrides, and the phosphides. And an easy way to remember that is going to be North Carolina Highway Patrol, or NCHP for short. So all of these 4 binary salts are going to be what we call water reactive. Oops. And you may see it as a symbol like that, a W with a cross going through it. Okay? What that means is whenever I add water to them, I'm going to produce some type of gas that's either flammable or toxic. So with my nitrides, if I add water to them, I'm going to get ammonia gas. Okay, NH3, and that's called ammonia gas. It's toxic, it's corrosive, it's flammable if it's in a high enough concentration. And I'm going to get rid of this real quick. Alright, so my carbides, I'm going to get C2H2, also called acetylene, highly flammable. Alright. Oops. And with my hydrides, I'm going to produce hydrogen gas, which is really flammable. You can think of the Hindenburg disaster if you want to think about what happens when hydrogen catches on fire. And you can also produce something called phosphine gas, which is pH3, which is highly toxic. Okay, so those 4 types of binary salts you got to worry about. Okay, so on your homework, they're going to be, whenever it asks for your hazards, you're going to list that it's water reactive, and you can list what type of gas is being produced. Okay, those are the water reactive binary salts. Okay, NCHP. Alright, so let's do a few more examples. Let me get rid of all of this. Let's start with a blank slate. And what about sodium fluoride. So I look on my periodic table for sodium and I see that it is Na. I look for fluorine, not fluoride, I look for fluorine on my periodic table and I see that it is F. Alright, so sodium is in group 1 on my periodic table, so I know it's going to be a metal with a +1 charge. And fluorine is a non-metal in group 7, so it is going to have a -1 charge. Alright, so all I do is I crisscross and I end up getting NaF. As easy as that. Alright, and because my because my non-metal is not one of the NCHPs, I know that my hazards are going to be variable. I'm going to have to look into what my hazards are going to be. I'm going to have to research it. I can't just predict that it's going to be water reactive or anything. Okay? Alright, let's go to another example. So let's do sodium sulfide. So sodium sulfide. Alright, so I look at my periodic table again and I see that sodium is Na in group 1 and that sulfur is my nonmetal in group 6. So my sodium, since it's in group 1, it's going to give up electrons and it's going to end up with a +1 charge. And my sulfur, since it's in group 6, we can give it a -2 charge. Okay, so just like we've done before, we're going to do the crisscross method, and what we end up with is Na2 S1, and we can get rid of that 1 and just call this Na2S. That's going to be our final answer for that. And again, because we have a sulfide and it does not fall into that NCHP, we are going to be able to say that it has variable hazards, which on our homework we can just write as VH, variable hazards. Okay? So the next one that we are going to do is going to be calcium nitride. Calcium nitride. Alright, so again, we're going to look at our periodic table, find calcium, find that the symbol is Ca, and it's going to be in group 2. So since it's a metal and it's in group 2, we know that it's going to be a positively charged cation with a +2 charge. Alright, and then nitrogen is going to be a non-metal, so we know that it's going to accept electrons, and since it's in group 5, we're going to give it a -3 charge because it needs 3 more electrons to meet that octet rule. Okay, so we're going to do our crisscross method, handy dandy crisscross method, and we are going to get Ca3 and 2 as our final answer for this. Okay, so the hazards for this, all right, I look at nitrogen or nitride, and that should ring a bell. That's one of the NCHP. Okay, so this is going to be water reactive and it's going to produce ammonia gas, okay, which is corrosive, toxic, and if it's in a high enough concentration, it can catch on fire too. Okay, all right, let's do another example, and this time we're actually going to go in reverse. Okay, so on your homework, sometimes I'm going to give you some problems that I give you the formula and I want you to name the stuff. So we have to kind of work in reverse on these. So if I give you Al to S3, all right, what we're going to have to do is we're going to have to take these subscripts and turn them into superscripts by kind of doing some reverse engineering on this, a reverse crisscross method. Okay, so my Al is is going to have a +3 charge, okay? And aluminum is a metal, all right? It is going to give electrons, even though it's kind of close to the nonmetals on the periodic table. It's still going to give up. It's easier for it to give up 3 electrons as opposed to receiving 5 electrons to reach the octet rule. It's kind of the path of least resistance to give up 3 electrons. And then my sulfur is going to have a -2 charge since it's in the group 6 category. So it just needs 2 more electrons in order to have its octet rule satisfied. So easy as that, okay? So I see Al, all right, and that is going to be aluminum. And remember, when I'm naming these, my nonmetal doesn't keep its original ending. It turns into ide. So this is going to be aluminum sulfide. And my hazards for this, because sulfide doesn't, it isn't one of the NCHPs, I'm just going to have variable hazards like that. All right, let me delete this, get a clean workspace. All right, next one is going to be BAS. Okay, so let's assume that we have subscripts there, and let's try going like that. All right, so I end up with Ba +1 and S -1. But hold up, I look at my periodic table, all right, and I find barium, and I see that it is in group 2, okay, so it can't have a +1 charge. And I look at my sulfur, and I see that it is in group 6, so it has to have a -2 charge. It can't have a -1 charge, okay? So what I can do is I can rewrite this top one. Instead of having a subscript of 1, if I had Ba2S2, okay, and I did my reverse crisscross, I would end up having Ba +2 and sulfur -2, okay? You can disregard that little plus sign. That's just if we were to combine these, okay? And I'm able to name this barium sulfide because now I have the right charge. Just like the last example, because my sulfide is not in the NCHP group, I can just give it variable hazards. So I'm going to have to look it up, okay? All right, and one final example is going to be Li3P. All right, so I can draw a 1 there because I'm assuming that there's a 1 there, and I'm just going to crisscross or reverse crisscross like I've been doing. All right, so lithium is going to have a +1 charge. I checked my periodic table. Sure enough, lithium is in group 1 on my periodic table, so it's going to have a +1 charge. And I have phosphorus, which is going to have a -3 charge. I verify that by looking at my periodic table, see that it's in group 5, which means that it needs 3 more electrons in order to satisfy that octet rule. So these are good. I'm good to go with these. So I can name this lithium phosphide. And phosphide rings a bell. It's in the NCHP group, so it is going to be water reactive. And when I add water to lithium phosphide, I'm going to get phosphine gas, okay, which is very toxic, very hazardous, okay? So before we finish binary salts, let's talk about transition metal cations. You can find all of the transition metal cations on page 3.8 of the lecture notes or supplement 3C. The transition metals listed in the table are going to have multiple potential cations that we can use. Each cation is going to have specific names, one being the older version and the other being the systematic version. You'll find both naming schemes out in the field. All right, so we're going to start with copper 1 fluoride. Copper 1 fluoride. Most of the time you are going to see that 1 as a Roman numeral like that, but you can occasionally see it just as a regular 1. Alright, so what we're going to do is we're going to start with copper, which is Cu, and the great thing about these is when I give you the name, you already know what the charge of the metal is going to be. So because there's a 1 up there, I'm just going to call it Cu plus 1. Alright, I find fluorine in my periodic table, and I see that it has a -1 charge. Since it's in group 7, it needs one more electron to meet that octet rule. So then, just like before, I'm going to do my crisscross method, and I'm going to end up with CuF. Okay, and because it's not one of the NCHP binary salts, it's just going to have variable hazards. Okay, so another name that I can give this, the old school name for it, is going to be cuprous fluoride, which you can find on your tables. Okay, copper 1 fluoride and cuprous fluoride are same thing. Alright, so let's go to next example, is going to be copper 2 fluoride. Again, I'm using those Roman numerals. Copper 2 fluoride. Alright, so I have Cu. I know what my charge is going to be. It's going to be +2, and just like last time, F is going to have a -1 charge. So I do my crisscross, and this time I get CuF2. Okay, and this is also going to have variable hazard since it's not an NCHP. So that doesn't necessarily mean that it is going to have all of the same hazards as copper 1 fluoride. Copper 1 fluoride and copper 2 fluoride are going to be different. I have CuF2 here, and then I have CuF for cuprous fluoride, or I should say copper 1 fluoride. Okay, so you have to be cognizant that those are not going to be the same. Alright, so another name that I can give this based on my table is going to be cupric fluoride. Okay, and a trend that you can notice on that table is that the us ending, okay, on your transition metal is going to be the lower of the two charges, whereas the ick is going to be the higher of the two charges. Okay, so next example, we are going to do mercury 2 chloride. Alright, so I find mercury in my periodic table, and it's going to be Hg, okay, which is kind of weird. Hg for mercury, it's old school naming system, okay? And I have a 2 as my Roman numeral, so it's going to have a +2 charge. And my Cl, I look at my periodic table, it's going to have a -1 charge, okay? This is getting pretty repetitive, okay? You guys are probably starting to see the trends. You're starting to realize, hey, I know where fluoride is. I know where, I know where fluorine is. I know where chlorine is, stuff like that, okay? And the more reps you guys do, the more second nature it's going to become. Anyway, I do my crisscross method. Alright, and I end up with HgCl2. Alright, and if I look at my table, another name that I can call this is mercuric chloride, using that ick because it is the higher of the two potential charges for mercury, and chloride is not one of the NCHPs, okay? So a lot of people always mess it up. They think that chloride is the C in NCHP. That is carbide, okay? Carbides are wire reactive, chlorides are not, okay? So my hazards for this are just going to be that they're variable, okay? So let me refresh my workspace and we'll do a couple more examples. All right, so if we have stannic sulfide, sulfide, sloppy spelling. All right, if I have stannic sulfide, I look at my table and I see that stannic corresponds with SN with a +4 charge, because that +4 is going to be my higher of my two charges for tin. Sulfide, my nonmetal, is always going to have a charge of -2, and so I can do my crisscross and I get SN2 S4. Alright, so if you see something like this where I have 2 and I have 4, I can divide that 2 into 4, okay? So I can reduce these down to SN1, S2, and I can just get rid of that 1 because it's assumed to be there, so I end up having SN, S2, okay? Another name for this, because I have that +4 charge, is I can call this tin 4 Roman numeral sulfide. All right, keep on wanting to misspell sulfide. Okay, tin 4 sulfide, and that's one of those weird things you got to learn about tin being SN on the periodic table. All right, and again, because sulfide does not fall into the NCHP, I can give this variable hazards. All right, easy enough. Let's move on to another example. Plumbous bromide. All right, so I see plumbous. I look on my table and I'm going to write PB. Okay, and I look at my table again for my charge on plumbous, or lead is PB, is this chemical, all right? And it's going to be +2, okay? And I have BR, which is just going to have a -1 charge since it is in group 7. All right, I can do my crisscross method, and I end up with PB BR2, and another name for this is going to be lead 2 bromide. Okay, and a neat little association you can use with lead and that plumbous old school name is plumbing. Okay, originally plumbing was all about lead pipes and whatnot, and so that's the association that you can think of there. All right, and since these guys are not involved or not included in the NCHP group, these are going to have variable hazards as well. All right, and so we got a few more examples, and this time we're going to start out with our formula. So Fe2S3. All right, so like we did with just the regular binary salts, we're going to reverse engineer this whenever we have a formula and we're looking for the name. So I'm going to bring these up, and my Fe being a metal is going to have that positive in front of the 3, and my sulfur, because it's a non-metal, it's going to have a -2 there. Okay, so I look up Fe on my periodic table, and that's going to be iron. I see that my charge is +3, so I'm going to give it a 3 Roman numeral And my sulfur, since it is an ion, it's going to be iron 3 sulfide. Okay, and based on my transition metal table, I can also call this ferric sulfide. Ferric sulfide, with the ic indicating the higher of the two charges. +3 is greater than +2 for iron, so that's why I have ferric sulfide. Alright, so we're going to do S and S. Okay, and we can write our assumed subscripts down there. And we're going to get Sn +1 and S -1. Alright, and if you've been following along pretty closely and paying attention, you'll probably realize that this sulfur here should not have a -1 charge. It should actually have a -2 charge. So that means that actually I would have Sn2 S2 over here. So I can crisscross these and I get Sn +2 and S -2. Alright, which I look at my transition metal chart and I see that Sn indeed has a +2 charge, and sulfur, based on our periodic table, is going to have a -2 charge. Okay, so Sn is going to be 10, and since it has a +2 charge, I'm going to write out my Roman numeral of 2, and I'm going to write this sulfur ion as sulfide. Okay, and so another name that I can give this is going to be stannous sulfide. Stannous because it is the lower of the two possible charges for 10. Right? And because it's a sulfide, it's not one of the NCHPs. It's going to have variable hazards. Alright, on to the last example we're going to do. And it's going to be Hg3, P2. And we're going to reverse engineer this. Bring those up top. So Hg is going to have a charge of +2, and phosphorus is going to have a charge of -3. Alright, and that looks right to me. Phosphorus has a -3 charge since it is in group 5. It needs 3 more electrons in order to reach that octet rule. Alright, and so I see Hg is going to be mercury, and since it has a +2 charge, I put the 2 in Roman numerals, and I call this phosphorus ion phosphide. Okay, and another name that I can give it is mercuric phosphide, because that +2 charge is the higher of my two potential charges on mercury. And I look at the phosphide and I realize that that is one of my NCHP binary salts, and so this is going to be water reactive, producing phosphine gas. Okay, and that's all of the binary salts. So the next family of salts is the metal oxides, which is pretty similar to a binary salt, but this time we're using oxygen as the nonmetal. And we're going to name these just how we did with the binary salts, but the oxygen is going to become oxide. So let's start with sodium oxide. And look at our periodic table, we see sodium is Na, and since it's in group 1 and it's a metal, it's going to have a +1 charge. Oxygen, since it's in group 6, it needs 2 electrons to reach that octet rule, so it's going to have a -2 charge. And just like before, we're going to do our crisscross and get Na2O. Okay, now with this, with oxides, the hazards are if I add water to it, so add water, I'm going to get heat and I'm going to get a caustic solution. Okay, what that means is I'm going to have a solution that is basic, all right, and not simple basic, but basic in the sense of corrosive. It's going to have a high pH, which is something that you'll see later on in the text. For us, what that means is if I get it on my skin or if I ingest it or anything like that, it's going to cause serious chemical burns. Okay, so this is something that we have to be very cognizant of when we're dealing with oxides. Okay, so the next example, and all of these oxides are going to have that same hazard where I add water to it and I'm going to get heat and the production of caustic solution. Okay, so my next example is going to be magnesium oxide. And I look at my periodic table, I see magnesium is Mg, it's in group 2, so it's going to have a +2 charge. I have oxygen, it's going to have a -2 charge, and I do my crisscross, and I get Mg to O2, and I can reduce that further to MgO. Okay, and my hazards, like I said, my hazards for all of my oxides are going to be that heat and caustic solution production. Okay, so I go on to my next example. Is going to be potassium oxide, and I look at my periodic table. Potassium is going to be K, group 1. It's going to have a +1 charge. O, as usual, is going to have a -2 charge, and I do my crisscross and I get K to O. Alright, easy peasy. Alright, these are pretty simple after doing enough reps of these. Okay, so my next one is going to be calcium oxide. And so I'm going to have Ca with a +2 charge, O with a -2 charge, and I'm going to crisscross, and I'm going to get Ca to O2, and I'm able to reduce that to, I am able to reduce that to CaO. I'll be careful not to hit the eraser button. Alright. So I can do my reverse engineering and do Fe2O3. So I'm going to take my subscripts and turn them into superscripts. Alright, and so I'm going to get Fe with a +3 charge and O with a -2 charge. I know by now that this O with a -2 charge is going to be oxide, and I know that my iron is going to be in that transition metal chart, so I can call this iron 3 oxide, and because that 3 is the higher of the two charges on iron that I can have, I can also call this ferric oxide. Okay, and my common name for this, believe it or not, is good old annoying, frustrating rust. Alright, so my last example for metal oxides is going to be SnO2. Okay, so I reverse engineer this. Assume that's a 1 there, so I end up with Sn+2 and O -1, and kind of like some of the examples we've done doing reverse crisscross method, this should look odd to you. Alright, should throw up some flags. So actually what I'm gonna do is I'm going to multiply this by 2 times 2 in order to get, let me reverse crisscross that for you. So I end up with Sn plus 4 and O negative 2, which is good. I'm down with this. Happy face. Okay, so I end up with 10, 4 oxide. Okay, and I can also call this stannic oxide because it is the higher of the two charges that I can have with 10. Okay, so with this one, anytime I see an oxygen and I do my reverse crisscrossing and I end up with this -1 charge, that's when I need to start thinking, this is kind of fishy. I need to maybe do some tweaking, and I do that times 2 to get what I'm after, okay, which is ultimately going to be that -2 charge on my oxygen. Okay, so that's it for metal oxides. Now we're going to talk about something called complex or polyatomic ions. This is where multiple nonmetals are able to bond together to form a complex ion, also called a polyatomic ion since it has multiple atoms in it, and it's going to act as a replacement for a single nonmetal. A complex ion is going to essentially act like a single atom, and the charge of the ion is going to apply to the entirety of that complex. The complex ion as a whole is going to gain or lose an electron. Most of the time it's going to be gaining electrons, but we will talk about one example in particular where it loses an electron. And luckily we are still able to use the crisscross method with complex ions. So the first family we're going to talk about is going to be called the Hydroxide Salts. And this salt family is going to consist of a metal, kind of like the binary salts, so a metal bonded to a hydroxide complex anion, which is going to be an OH with a -1 charge all around it. So those brackets mean that that OH acts as a complex ion, and the whole entire thing is going to have a -1 charge. Okay, and we are going to name this how we did the metal oxides, but instead of oxide, we're going to put hydroxide at the end. Okay, hydroxide. All right. So the first example we're going to do is going to be potassium hydroxide. Potassium hydroxide, and as we've seen by now, potassium is going to have a charge of +1, and like we talked about up here, OH is going to have a charge of -1. And just like before, we're going to do the crisscross method, but we're going to crisscross everything over, or sorry, I shouldn't say everything, this +1 charge across the entire OH. So I'm going to end up with K, the OH in brackets, and I can ultimately just write this as KOH. Okay, so my hazards, luckily, are going to be the same as my oxides. Okay, so I'm going to get the production of heat and caustic solution for all of my hydroxides. Okay, let's go on to another example where I have sodium hydroxide. Alright, and sodium's going to have a +1 charge. Hydroxide is going to have a -1 charge. And I do my crisscross, and I get NaOH, which I can just write as NaOH like that. Easy peasy. Okay, let's do another one where let's do calcium hydroxide. So calcium hydroxide Calcium is in group 2 on my periodic table, and so I'm going to do Ca plus 2, and my OH, like I've seen before, is going to have a -1 charge. So I do my crisscross, and I get Ca 1. I don't have to write that 1, it can be assumed. I'm going to have my OH with a 2 out there, okay? And I have to keep that 2 applied to this whole OH complex, okay? So I can rewrite this. This is the more likely way you're going to see this written, is going to be Ca parentheses OH close parentheses 2, like that, okay? That's the way that you are most likely to see it as, okay? Where that 2 applies to that entire OH complex whenever I bring it down, okay? And a lot of people ask, well, would I be able to write it as, say, CaOH? OH, yeah, you could, but you're really not going to see it like that. You're never really going to see it out like that out in the field. This is going to be the most prevalent way, okay? So let's do one more example, and this time we're going to start with a formula first and then try to figure out our name. So let's do Al OH in parentheses and a 3 out there. Alright, so we can assume that there's a 1 out here, and we're going to do our crisscross. Alright, so we end up with Al plus 3 and OH with a -1 charge. Alright, Al with a plus 3 is just going to be aluminum. Alright, aluminum has that plus 3 charge. It's in group 3. It wants to give up 3 electrons, and when it does give up those 3 electrons to meet the octet rule, it's going to have a plus 3 charge, alright, since it doesn't give up its protons in the process. And my OH, as I've seen in this chapter, is going to have my -1 charge, so I'm going to call this aluminum hydroxide. Alright, and that's it for hydroxide salts. And the next family we're going to talk about that contains polyatomic or complex anions is going to be the peroxide salts. Peroxide salts. Okay, and these salts are going to consist of a metal plus a peroxide complex anion, which is going to be 2 oxygen atoms, so O2, and that is going to have a -2 charge going across it. Alright, and just like before with our salts, the metal is always going to be named first and in its entirety, and it's going to be followed by the word peroxide. Okay, so let's do some examples. Our first example is going to be sodium peroxide. Alright, periodic table shows us that sodium is Na with a +1 charge since it's in group 1, and we're going to write this peroxide O2 with a -2 charge. Okay, and I'm going to do my crisscross for this, and I end up with Na2O2. Okay, now a lot of people are gonna probably think, well, I have my Na2O2, I can just reduce that to NaO. And you can, but I tend to prefer leaving it just like that, because if I look at something like this and it's 3 o'clock in the morning, and you know, I've still got sleep in my eye and stuff, and I'm on a significant hazmat event and stuff, if I see that, my mind is going to think, that's just an oxide, okay? But if I see this, the O2 there, I'm going to think this is a peroxide, okay? And I would be correct. And one of the reasons why I need to be pretty accurate with my assessment of it being sodium peroxide is because my hazards for peroxides are going to be a little bit different than my oxides and my hydroxide. So I'm still going to get heat. I'm still going to get a caustic solution. But I'm also going to get a release of oxygen. So my oxygen is going to increase, okay? Which normally when my oxygen increases in the atmosphere, all right, that means that I am more likely to intensify combustion if I have something on fire. So I really don't want to, if I do respond to an incident and I have something on fire and I have, open container of sodium peroxide next to it, I really don't want to lob water on the sodium peroxide because I'm going to create heat, caustic solution, and I'm going to release that oxygen, which is just going to intensify that fire. Okay, so because of that release of O2, that's why I'm inclined to leave that O2 in the formula like that. Okay, and I tend to do that with all of these. All right, so my next example is going to be calcium peroxide. And calcium is going to be in group 2, so it's going to have a +2 charge. Peroxide is going to have a -2 charge, O2 with a -2 charge, and I'm going to crisscross these as before, and I get Ca2, O2 with my subscript there. Now, in this case, all right, I can cross these out, reduce them down, and I get CaO2. All right, and I'm fine with that because I still have this O2 in the formula that's able to tell me at 3 in the morning, hey, this is a peroxide. Okay, don't add water to it. You're going to get heat, caustic solution, and the release of oxygen. Okay, so that's why I leave that there. Next example is going to be aluminum peroxide. Aluminum peroxide. And aluminum is going to have that +3 charge. Peroxide is going to have -2 charge. So I'm going to crisscross, and I end up with Al2, O2, 3, and I can replace those brackets with parentheses, which is how you're more likely going to see it. All right, and that's how this is the form that I'm most likely to see it as. Now, you could potentially see it as Al2O6, where you multiply that 2 there by the 3, and it could be even further reduced down to AlO3. But again, like I was saying earlier, when you leave that O2 in there, all right, you'll remember that it's a peroxide. Okay, at least I do, and I would recommend that you do it too. That's how you're more commonly going to see it in different chemical literature and stuff when you're doing research on a scene. That's how you're going to see it on Google, on Wiser, stuff like that. So I always leave it in that format. Okay. Okay, so our next example is going to be stannous peroxide. So remember from our transition metal chart that stannous is going to be Sn +2 or 10 +2. All right, and our peroxide is going to be O2 with a -2 charge, and we do some crisscross action and get Sn2, O2, 2, and I can cancel those out to get SnO2. All right, and you probably are looking at this and thinking, wait, this can also be the same formula as stannic oxide, not peroxide, stannic oxide, which it can be. Okay, so stannic is +4, and I have O -2. Do my crisscross, and I end up with SN2O4, and reduce that down to SnO2. Okay, now how I'm able to differentiate these. If you go into a warehouse or something and they have stannous peroxide in there or stannic oxide, and you really don't know what it is because all they have is the formulas written on the container for some reason. Okay, what you can do is remember that your peroxide is going to release oxygen when there's moisture in there or whenever there's water. Okay, whereas SnO2, stannic oxide, is not going to do that. So I could take my 4-gas meter, all right, and if I start getting an increase in oxygen, I'm going to know that it's the peroxide versus the oxide. Okay, so that's just something to be cautious of whenever you're dealing with some of these formulas, especially if they're just stenciled or spray painted on to a canister or a drum or anything like that. Okay, not everywhere that you're going to respond to is going to be pristine lab settings. Some of them are going to be very clandestine and very crummy and stuff like that. So just beware that you might have to do a little bit of digging with your meters to figure out exactly what something is. Okay, so that is my peroxide salts. Next is going to be my family of cyanide salts, and these are going to be formed by a metal and a cyanide complex anion. Okay, and that cyanide is going to be Cn all together with a -1 charge. Okay, and just like all the other salts that we've been doing, we're going to name the metal first in its entirety, followed by the word cyanide. Okay, so if I have sodium cyanide, I'm going to have Na with a +1 charge, and I'm going to have Cn with a -1 charge, and you know the drill. I do a crisscross method, and I get I get Na1, Cn1, and because all of that is ones all across the board, I can just call it NaCN. Okay, my hazards for these, as you can probably figure out, is these are going to be highly toxic. Okay, highly toxic. That's going to be my main hazard associated with these. Alright. Next one is going to be potassium cyanide. Alright. Potassium is going to have +1 charge. Cn is going to have a -1 charge. And I do my crisscross, and I get KCN. Alright, one final example. I have aluminum cyanide. Aluminum is in group 3, so it's going to have a +3 charge. Cyanide is going to have a -1 charge, and so I do my crisscross, and I get AlCN with a 3. Put my little 1 there, and I can rewrite this as Al parentheses Cn close parentheses 3. That's it for cyanide salts. Alright, the next family we're going to talk about is the Oxysalts, and I'm not going to lie, these can be pretty intimidating at first. but after enough reps, you shouldn't have any issues with them. These consist of a metal and an oxyradical, also known as an oxyanion, which is just going to be two or more elements. One of them is going to be oxygen, and they're going to act together as a single unit, kind of like what we saw with hydroxides and cyanides and peroxides and stuff like that. When naming these, just like with the other salts, you're going to name the metal first in its entirety, and you're going to follow that with the appropriate name for the oxyanion. And the complicated thing is that the name of the oxyanion is going to depend on how much oxygen it has in it. To help you with this, you can find the oxyradical chart and the naming configuration on page 314 and also in supplement number 3B in the supplement section. All right, so our first example is going to be one called sodium chlorate. All right, and sodium is going to be the same as what we've been working with, where I've got Na and I've got a charge of +1, and my chlorate. So what I'm going to do is I am going to go into that oxyradical chart, either on page 314 or supplement 3B, and I'm going to look at it and find chlorate. And if I find chlorate, I'll see that it is labeled as what's called a base state. So that's kind of like my home base whenever I'm talking about oxyradicals, okay? And my chlorate is going to be ClO3. I can put some brackets around that. And if I also look at my table, I see that it has a -1 charge all around that, okay? And so just like what I've done before, I'm going to do my crisscross method, and just like with the other polyatomic ions, I am just going to distribute that across the whole deal, and I can get rid of those brackets, and that is sodium chlorate. Okay, so what about if I have sodium perchlorate? So if I have perchlorate, I have my sodium there, and I look at the word perchlorate, all right? So I don't see perchlorate in that chart, but I do see chlorate, okay? So I can write that out, okay? But if I look further down on that chart, I see that per means that I'm going to have one more oxygen, okay? So instead of the 3, I'm going to have a 4 there, okay? I'm going to have one more oxygen than my base state. And so my charge stays the same, so I'm going to have -1 there, and I can get back to doing my crisscross, and I end up with NaClO4. Okay? All right, let's try the other way, where I have sodium chlorite, and I'm going to have Na+1, and again, I don't see chlorite as my base state. I don't see chloride in my chart, I should say, but I do see chlorate. All right, and again, that's going to be ClO3, and because this is chlorite, my chart tells me that that is going to indicate that I have one less oxygen than my base state. So instead of ClO3, I'm going to turn that into ClO2, and it's still going to have a -1 charge. And so I'm going to do my crisscross and end up with NaClO2. All right, and you guys should be able to understand that I'm not including my brackets in here just because the ones cancel out, okay? Just to clarify that. And then finally, I have sodium hypochlorite. This is the chemical name for bleach, which you would find in Clorox. And I'm going to have Na plus 1, and I start out with ClO3 like I have been before, all right? But that's not what I have. I have hypochlorite instead of chlorate, and so according to my oxyradical charts, I would get rid of that 3, and I would just have, oops, let me get back to my drawing, and I would have ClO, and all of that is going to have a -1 charge. And I do my handy dandy crisscrossing, and I end up with NaClO. Alright, so you can see there, I started with sodium chlorate, my base state. Alright, if I add one more oxygen, alright, then I go to perchlorate. If I take away an oxygen from my base state, I end up with chlorite. And if I take 2 oxygens away, I end up with sodium hypochlorite. Okay? Now, my hazards for all of these are really the primary hazard that I'm focused on with all of these oxysalts is that they are potent oxidizers. Okay? And we kind of talked a little bit about a similar effect with the peroxides whenever it releases oxygen when it comes into contact with water. With oxidizers, these don't necessarily burn, but if it's in the vicinity of something that is burning, your oxidizers are going to intensify that combustion, okay? And so that is something that we have to be worried about. They don't like to interact with fuels and whatnot. You may have something like diesel fuel, and you could mix it with ammonium nitrate, which we'll talk about in a little while, and diesel fuel is something that's pretty, not too terribly hazardous. I mean, we use it in vehicles all the time, but you mix it with ammonium nitrate and you add a good bit of energy, and now you have a pretty solid explosive. That's what they used in the Oklahoma City bombings. So anyway, we'll talk more about ammonium nitrate here in a bit. We are going to do a few more examples though. So let's do potassium nitrate. And our metals, from here on out, our metals are going to be pretty easy. We've done plenty of metals so far, so that's going to be K with a +1 charge since it's in group 1. And nitrate, all right? I see this 8 ending, which indicates that it is going to be my base state, so it should be on that table, okay? And I find it. It is going to be NO3, and that is going to have a -1 charge. And just like I'm so used to doing now, I do my crisscross, and I get KNO3 with my 1 subscripts, and I can just write that out as KNO3. Okay, easy as that. All right, so let's move on to another one where I have aluminum nitrite. All right, Al +3, and I have my nitrite. All right, since it's not an 8, it's not going to be my base state, but I look at my table and I see that ite indicates that I have 1 less oxygen than my base state. So if NO3 is my base state, nitrate, then nitrite is going to be NO2, and that's going to have a -1 charge. All right, and so then I can simply do my crisscrossing, sure you guys are getting tired of seeing all these red and green colors as if it's Christmas time. This is being recorded in July. And I get AlNO2 all in parentheses with a 3 outside, okay? That is aluminum nitrite. Alright, on to another one. So, calcium hypochlorite. This is the common name for pool shock. Calcium is going to have a +2 charge. Alright, hypochlorite. Alright, so I don't see chlorate in here at all, but I do see chlorate in my base state chart. Alright, but in order to get it to hypochlorite, I have to remove 2 of those oxygens from the base state. So instead of ClO3, I'm just going to have ClO, and remember for these, it doesn't matter how much oxygen I lose, or if I add the oxygen, my charge is still going to remain the same. So I can come in here and crisscross, and I get I get Ca parentheses ClO close parentheses 2 as calcium hypochlorite, otherwise known as pool shock. Okay, a couple more examples. So let's go in the opposite direction just for fun. So let's have K2SO4. Alright, so how I tackle something like this where I'm going in the opposite direction. Alright, so what I do is I kind of separate this. Okay, so I have potassium with that 2 subscript, and I have this entire thing, SO4, with just a 1 subscript. Okay, so I reverse engineer it. I get potassium with a +1 charge, which works for us. We've seen that over and over and over again, that potassium is always going to have a +1 charge. My SO4 is going to have a -2 charge, and I can look at my oxyradical chart and see if that makes sense, see if I can find anything in there, and sure enough, I see that this is going to be called sulfate because it is the base state, okay, and this is going to be potassium. So my name for K2SO4 is going to be potassium sulfate. Alright, and we'll do one last one of these. Alright, we're going to have Ca3, PO4, 2. Alright, and again, we are going to reverse engineer this thing. So I'm going to bring my 3 up to the top, I'm going to bring my 2 up to the top on opposite sides, and I end up with calcium with a +2 charge. I'm good with that because calcium on my periodic table is in group 2 and it's a metal, so it's going to have a +2 charge. And I'm going to have this guy over here, PO4, with a -3 charge since it's an oxyanion. And I look at my oxyradical chart and I see that PO4 -3 is in fact on there. It is a base state. Okay, in fact, it is called phosphate. So this is going to be calcium phosphate. All right, and to go even further, if I had Ca3, let's say PO5, 2, I would just reverse engineer that and have Ca +2, PO5, sulfide with a -3 charge. All right, I saw that phosphate was my base state with 4 oxygens. So if I add another one to that, it's not going to be phosphate, it's going to be perphosphate. Perphosphate. Calcium perphosphate, to be exact. All right, I hope that makes sense. So the last family that we're going to talk about today with the salts is going to be called the ammonium salts. And the ammonium ion is the only complex cation. So it's the only complex ion that is positively charged. And what it's going to look like is NH4, all with a +1 charge. So we've been talking about complex anions that have some type of negative charge, and this is a complex cation that has a positive charge, a +1 charge. Okay, and since it has a +1 charge, it's going to act like group 1 metal. All right, when we're figuring out our formula, so it's going to be similar to sodium and lithium and potassium. Okay. The hazards of an ammonium salt is mostly going to depend on the non-metal attachment. So if I have an oxy radical, then it's going to be an oxysalt. If I have one of the NCHPs of binary salts, then it's going to be water reactive and produce some toxic or flammable gases. If it's a hydroxide, it's going to produce heat and caustic solution whenever I add water to it. Okay, so the hazards are going to ultimately depend on that non-metal attachment. When we name these, we're going to name our ammonium cation and then the non-metal attachment. So this is going to be called ammonium. Okay. So let's start with our first example, and it's going to be ammonium chlorate. And so we're going to start with NH4 with a +1 charge, and we're going to have ClO3 with a -1 charge, okay, because I have chlorate and that is going to be my base state. All right, so I look at my oxyradical chart, I see ClO3 is there and it's going to have a -1 charge. So all I do is use Old Faithful, my crisscross method, and I end up with NH4 with a 1 coefficient, ClO3 with a 1, cross that out, and I get NH4 ClO3. Because that is a oxy radical, this is going to be an oxysalt, and it's going to be an oxidizer. Okay, all because of that oxyanion there. Okay, so my next example is going to be ammonium sulfide, and so you can use brackets and parentheses interchangeably, it's fine. And sulfide, all right, I look on my periodic table for sulfur, all right, and I see that is going to have a -2 charge because it is in group 6, so that means it needs 2 more electrons in order to be satisfied by that octet rule. Okay, so I do my crisscross, and I get NH4, 2, and my S out there. Okay, so in parentheses NH4, close parentheses 2, and then my S. And because my sulfide, okay, indicates that it is like a binary salt, or the non-metal in a binary salt, and it's not one of the NCHPs, my hazards are going to be variable. Okay, so I'm going to have to look it up. And my last example is going to be ammonium nitrate, which we had briefly mentioned this earlier. So again, I start out with my ammonium cation. See the 8 at the end, so I look at my oxyradical chart, and sure enough I see nitrate in there, and it is listed as NO3 with a -1 charge because it is a base state. Okay, I do crisscross, get NH4 1, NO3 1, mark those out, get rid of the parentheses, and I end up with that. Okay, because I had an oxyradical, this is going to be like an oxysalt, so the hazard is going to be that it is an oxidizer. And this is a pretty notorious oxidizer at that. Ammonium nitrate has been used many times either as a weapon of terrorism or just as an accidental explosive or as an intentional explosive. Anyway, it has a pretty prolific history in the hazmat world. Probably the most recent explosion was in Beirut, where I believe it was well over 2,000 tons of ammonium nitrate detonated and killed a lot of people. I mean, well in the hundreds. And then West Texas was in 2013, and it killed over a dozen people. It was in a fertilizer plant. The fertilizer plant caught fire, and the ammonium nitrate that they had in the fertilizer plant got heated up and contaminated by the soot, and ultimately there was a detonation, and it did a lot of damage. And most recently, on January 31st of 2022, I actually got to respond to an ammonium nitrate call. It was in Winston-Salem here in North Carolina, and it was at the Weaver Fertilizer plant on the north side of Winston-Salem. And essentially they had about 450 tons of ammonium nitrate in a large warehouse-style building. The building caught on fire, and so the concern was the ammonium nitrate inside, but there was also a rail car adjacent to the building that had about 80 tons of ammonium nitrate contained in it. And so luckily Winston-Salem had a history with this location, and they chose to operate defensively, just lobbing water on the place. Every firefighter was evacuated outside of a mile radius of the place, and they called Greensboro's regional response team. I was working that night, and I responded. And I'll tell you, when you're setting up a 1 mile radius on some of the software that we have, it really hits home how significant that is. I mean, you're evacuating 20 to 30,000 people in that area, and luckily we got very fortunate that it didn't detonate. There were no injuries, no deaths, anything like that, and we think it was because the ammonium nitrate in the rail car was it was not exposed. It was not in the open air, able to get contaminated by the soot and whatnot. But Winston-Salem did a heck of a job of getting everybody out there, and I think Greensboro's regional response team did a heck of a job kind of doing some advanced work on our end to set up plume models and evacuation zones, and ultimately doing air monitoring. And fortunately, we did not become a tragic part of history. We were a success. So anyway, that's all for ammonium salts, and with that, that's it for salts in its entirety. until the final exam, of course. You can find all of this information that we've talked about today on the charts in Supplement 3. And if you have any questions, feel free to contact me. Take care, and in the next video, we're going to be talking about inorganic non-salts. So, see you then.